Okay. All right, let's try this again. So, all right, so back to our discussion on microscopic momentum transport. Again, we will work through most of the chapter 1. So Newton was the first one to formalize discussions on viscosity. If I have two plates, one of them is keeping still, and the lower one is at the constant velocity Vx. After some time, I will establish a linear profile, and basically I will change from 0 to Vx in a linear fashion. So if I want to formalize this plate area and plate area given as A and Y being plate separation, I'm actually going to, if I think about the force needed to maintain this profile and basically pull this lower plate at constant velocity, that force is of course proportional to the velocity. I would expect that. It's inversely proportional to the plate separation. Okay, so the larger the plates, higher the larger the separation, smaller the force. And then it's also proportional to the area of the plates. So when I actually put that together, and I normalize it by area because I don't necessarily always know the area, then this force per area, this is what I'm going to be referring to as shear stress, okay, is proportional. So my coefficient of proportionality we will refer to as mu, to the difference of velocities divided by, so basically this is my velocity Vx, but if I had any other situation where possibly I have the upper plate moving as well, then I would be looking at the difference between the two velocities. Okay? So basically that's the difference between the two and the separation between the plates. So if I look at this as just in the coordinate system, okay, we like orienting things in the coordinate system, then my upper plate in the direction of the coordinate system is actually moving at 0, and the lower plate is Vx. So this is what introduces the negative sign in this relationship. And the part of the reason why I always have a negative sign is the fact that in nature, things flow from higher potential to lower potential. Every coordinate system that I know of points from lower to higher values, right? So all coordinate systems, they start at 0, for instance, and they point in the direction of larger values, right? So my coordinate system naturally points from smaller to larger, whereas any kind of flow, equalizing anything in nature, when I have gradients at work, it's always flowing from larger to smaller. So typically in most of these relationships, when you look at the vector forms, because this is ultimately going to be a vector relationship, so vector has a direction, you're going to have a negative sign there for that reason. Because again, coordinate systems, they go from smaller to larger. Nature works from larger to smaller. Okay? So that's going to essentially cause this negative here. So if I look at this, so this is a finite difference in this particular case. If I actually take this for any plate separation and take that separation to 0, okay, I'm actually going to get a derivative in y direction for my Vx. Okay? And I'm just going to hint now that one thing that we have to be aware of is that velocities that we are macroscopically looking into are in x direction. Okay? The transfer is happening in y direction. Okay? So it's basically that something is happening, this momentum transfer is going from this plate on the bottom to plate to the top. That's in y direction. Okay? And this is why we're saying this is tau yx. And this is going to be the cause, so this is also why we're calling it shear, okay? Because obviously the transfer is happening by this, not by this, okay? So I'm not pushing like this is normal direction, okay? I'm actually shearing layers of fluid, and they're acting at each other like that, transferring my momentum upwards, okay? I'm not transferring momentum this way. So that is an essential observation here. And this is also how we're going to actually fill up this tensor in all directions. So we will later going to look at transfer of all possible velocities. Right now, my Vy and my Vz are 0. So there's no difference to transfer. Okay. But if I had velocity that is Vx, Vy, Vz, it has all three components. All three of those components could transfer, if I had gradients in all directions, all of those could transfer across all possible planes, not just y. So I could have a transfer of Vx, Vy, Vz across the planes in x, y, and z direction. And therefore, we will actually fill up a tensor, the shear stress tensor later on. So this tau right here, this is a Greek letter tau, will actually be a tensor. It's going to have 9 components. But for now, we're just looking in one direction because we actually have to get the feel for it first before we generalize. All right. So the direction of the force, as I noted, the direction of the force is actually in x direction, but it's transferring across in y direction. So we're going to introduce notation. The way I'm going to talk about it is that this force is exerted by lesser y portion. This is this blue right here. That's my lesser y portion of the fluid on the greater y portion of the fluid. And again, reasons to introduce this lesser, greater, and so forth will be these directions and positive and negative signs that I'm going to have in formulas. Okay? So momentum is actually transferring in y direction while the force itself is in x direction. So I have this two views, so to speak. There's a force view and there's a momentum transfer view. Okay? So I can look at it at a force. I'm literally pulling something in this direction. Or I can look at the molecules here, little molecules here all over the place, are having larger momentum because of their x velocity, okay? And they're colliding with all of the molecules above and below them. And basically the larger momentum of the molecules here will transfer through those molecular collisions upwards. So again, my momentum transfer is upwards, but my force is acting in parallel directions. So just there are two possible views of looking at it, and sometimes it's better to look at it one way or the other, depending what it is that you're analyzing. Okay. Right. So this is my force perspective. My tau yx is the force in x direction exerted by this box of fluid that I'm going to talk about as lesser y box of fluid, okay, onto the greater y box of fluid. And we will later on introduce different coordinate systems. So we will actually have in cylindrical coordinate system, I'm going to have lesser r onto greater r. So it can work in any coordinate system. Okay. So I'm just looking at the lesser coordinate versus the larger coordinate. Okay. Per unit area. So basically I divided this force per unit area. And since I'm going to have velocities, there is actually unit time there, but it's actually units are force per unit area. Okay. But there's a time transfer in there because it's velocities that I'm transferring. Now, momentum perspective is the x momentum of particles. So basically, momentum due to the velocities in x direction. Okay, I'm going to refer to that as x momentum. So x momentum of particles in positive y direction is transferred in positive y direction per unit area perpendicular to that y direction. Okay? So again, flux happens because I have these neighboring fluids have different velocities, so larger momentum in one of the layers will transfer to the smaller momentum region in different other layers. And this x momentum is transferred by molecular collisions. So if I look at tau yx with this view, okay, I can actually look at it as a difference in momentum, though typically we think about rho as constant for most applications that we will look into. We will look into the fluids where we assume that their density is constant. So basically, because of that, I can basically multiply and divide by rho and actually then look at this as a derivative in momentum. Okay, it's the same as derivative in velocity. Okay? And then I can actually look at the tau yx. This is going to be, if I divide my original mu, I divide it by rho, I'm going to get kinematic viscosity. And this is a difference or derivative of momentum. So this is sort of like a momentum view. So this is how I defined it, and I can look at it in this way. So this is interpreting the original force perspective as a momentum perspective. Does that make sense? So this is just different views. And then there's one more popular view that actually comes up in all kinds of engineering modeling. And this is resistance perspective. And it comes, of course, from electrical circuits. Okay? But you can pretty much model anything and everything as transfer of something, and you kind of measure the resistance to that transfer. Okay? So the gradient of velocity is typically in that view flux of anything is driving force divided by resistance to it. Now resistance in this case I would just define as 1 over viscosity. Okay? So this would be molding what I told you into this resistance perspective. Okay? So if I have a pipe, instead of looking at viscosity, which was coefficient of transfer, okay, between the forces and the transfer of momentum, I'm just going to look at the 1 over mu as a resistance to my fluid transfer, and then I can fit it into the electrical circuits view, if you will. Okay. And again, my driving force is gradient in velocities, and resistance to it is 1 over mu. Okay. All right. So Newton's law is only one out of a number of very popular laws that relate flux of a quantity, okay, and the appropriate gradient that you could also see as this driving force for the whole transfer in some sort of linear way. So I have a linear coefficient that is built within. And all of these laws are actually, somebody looked at it, Newton and many other very famous researchers in the past. They basically looked at something and said, well, it looks that I have a proportionality there. I'm just going to stick in a coefficient, and then I'm going to worry about measuring. Okay? And then my measurements in most cases, they have actually confirmed that this law works. Okay? So this is this idea that I played you or attempted to play for you last time. I don't know what was the how successful it is and whether people in the back actually heard it. But basically, Richard Feynman said you first guess by observing nature. You make a guess. That is essentially your scientific hypothesis. Okay? And then you actually figure out, well, okay, if this guess is really true, this is what I should be seeing. And then you go measure and see whether you see what you expected to see. And if you did, you essentially confirmed your hypothesis. And if you don't, you kind of move on and make another hypothesis. In either way, you actually learn. So there is this comparison to experiments. You could also discompute the consequences can be actually interpreted as theoretical view. So you make certain assumptions. Okay? And you find whether you can confirm your observation, which is kind of from the outside of the box. So it's in essence upscale. Can you go to something more fundamental, for instance, molecular theory, and see whether you can actually find out whether the same law holds. And we will actually do that. So in that case, you will have confirmation that is theoretical, you will have confirmation that is experimental, and as in the last 50 years or so, we're also looking for confirmation in computational ways. Okay? So you could actually do simulation that, given certain assumptions, could actually confirm whatever it is that you hypothesize as well. So these are three different ways to actually see whether your hypothesis works. Yeah. So most of the, again, empirical laws were sort of like guesses that ended up being confirmed by experience. So one of those laws is Fourier's law, okay? And again, in this case, we're going to have transfer of heat, and I just kind of gave the year for your basic idea. So Newton's law was 17th century, and now this is 19th. So yeah, if I have two plates again, but they're kept at two different temperatures, okay? Now I will have the transfer because of the gradient in temperature, okay? So my driving gradient or driving force is difference in temperature. And basically the amount of heat being transferred per area is again proportional to this difference or gradient in temperature. Okay? So my K, or the coefficient in this case, is called thermal conductivity. So there are similarities that we can actually observe between the two if I think about it. So I have, for momentum, actually, can you try to fill this table up? So draw up a table on your piece of paper. Sort of review of things that I've said. So in my momentum transfer, potential differences in velocity. So we looked at Vx, but in general, it's actually V as a vector, okay? So that has components Vx, Vy, Vz. And I can look at that difference or gradient as a driving force, okay? And flux quantity, how do I refer to it? Shear. So we actually had a letter for it, tau. Tau yx, if it's just that simple situation that we looked at the very beginning, but as a general, it's actually a tensor tau. Okay, so it has 9 components, and my transfer coefficient is viscosity, which we refer to as mu, or sometimes you will actually have, if you normalize it by density, then it's kinematic viscosity nu. Okay, now in heat, I will have potential difference in temperature, and my driving force is that gradient of temperature, and the flux quantity is then Q. We refer to it as Q, and it's actually simpler because temperature in itself is a scalar measurement. It's not a vector measurement as velocity is. Okay? So it's going to look simpler, and this flux quantity will be a vector in result. Okay? Because this temperature difference I can transfer in x, y, and z direction. Whereas in momentum, I have these three possible velocities that are to transfer in x, y, and z direction that results in a tensor. And we're going to go through that in more detail later. And my transport coefficient is K, or thermal conductivity. Okay. So again, we will first operate just with Vx, but in general, bear in mind that basically my velocity is a vector. All right. So another law from the very same family of linear laws, and essentially the moment something is called a law, you can kind of assume its laws are those assumed most often, and they're typically first order. So if something is going to be a law, it has to be also simple enough, and that simple enough means a linear relationship. So the moment you have something called a law, it's widely applied, it's a first order approximation, and there's typically a linear relationship in there. So Hooke's law says, okay, if I stretch a spring, then restoring force trying to put it back into its original position is proportional to the delta x, where delta x is this enlargement of the spring. Now, if I actually look into this being a beam or a material rather than just a simple spring, then I will have still delta x, which is typically going to be very small, and my shear stress is still going to be this shearing force F divided by area. And I'm going to actually have a shear modulus G in there, and delta x divided by delta y will be a shear strain epsilon xy or xy. And this shear modulus for most of the material that we're interested in mechanics is typically in gigapascals, referring to the fact that it's much harder to deform solid material than it is to deform or flow fluids. Okay. So I guess I should mention it immediately that the key difference between fluids and solids is that fluids cannot be shear, they flow in response to shear, whereas solids deform in response to shear, so they're on two different scales of deformation. Okay, and then Fick's law is here as well. So this is now a concentration difference, okay? And I will have, let's say that I'm actually diffusing through a silica wafer, okay? And I keep concentration at two different ends of that wafer different, and I find a way to keep them constant, okay? Then the mass flux of something diffusing through that silica wafer, it could be helium, for instance, that's the simplest one, okay? Then I will actually have, again, that this flux is proportional, and D is my coefficient of proportionality called diffusivity. And I'm going to look at, again, a gradient in this concentration. Okay. So again, I have a very similar law, and again, I'm always flowing from larger to smaller, in this case, concentration, and that in itself is against a coordinate system, because coordinate systems point from smaller to larger. So I will again have this negative here. Okay. And then finally, in porous media, of course, we have Darcy's law, again a linear law. Okay. I'm going to look at now a difference in pressures, and the gradient in pressure is the driving force. Okay. Coefficient is composed of two things. One is geometrical characteristic of my pore space pathways, okay, and we refer to it as permeability. We model it as completely distinct from the fluid that is fluid, which is not flowing, which is not true, and in petrophysics you will actually learn of corrections that actually correct for that fact. But basically, if I measure permeability with gas versus liquid, I'm going to get different values. Okay? But the way it's envisioned as separate. Okay? And then my fluid simply scales here with its viscosity. Okay? And I'm again going to look at the volumetric flux of fluid coming out of a rock core or any kind of porous material, and that's again it goes against the potential difference. So I'm going to always flow from larger potential or larger pressure to smaller pressure. So again, this Darcy's law is the similar family of belongs to the similar family of laws. And finally, we get to electrical currents. If I keep a conducting rod at different potentials, in this case electrical potentials, then the current I divided by area, I'm going to look at that flux and call it J as well. This J is proportional to the difference in potential, and conductivity is denoted as sigma here. We will often look at the resistance, so sigma times area divided by the delta Y is actually 1 over resistance. So the so-called integrated version of this law is more famous. It says that potential is current times resistance. And that is what's most often called Ohm's law. Though this original formulation is basically equivalent to what we see in Newton's law, Darcy's law, and so forth. Yeah. So again, so let's now so now that we gave the context to all of these laws, let's get back to viscosity. So let's look at the units. You will have to be well versed in all of the units. SI system should be the system, but in petroleum engineering, British system prevails. So you'll have to kind of operate and be able to convert with in both. The back of transport phenomena has actually coefficients if you need quick tables to go from different units to the other different units. Though these days, I don't know how about you, I Google it. So essentially, you will be probably Googling it, but for exam, you have to know where the table is for quick conversions, okay? So you're not allowed to Google anything during the exam. Therefore, please make yourself familiar with the conversion tables in BSL, okay? Now, and again, you will be able to, now that I pointed out, I may as well, I will not ask you to know those by hand, by memory. So you will be able to have those tables with you or write them down on some sort of cheat sheet. So don't focus on memorizing, but certain common conversions are actually useful to know. So my coefficient viscosity is the shear stress tau yx divided by gradient in velocity dx. So my shear stress is in pascals, and gradient of velocity is meter over second times 1 over meter. Okay. Which basically is Pascal's second, or sometimes Newton over meter squared times second. Okay. So this is the SI system unit. Then in so-called CGS unit, that is actually more common, I have dyne divided by centimeter squared. And then if I look at the difference in velocity, that's centimeter over second times 1 over centimeter. So dyne divided by centimeter squared times second is so-called poise. The most common unit that you will see is centipoise, okay? Because viscosity of water is 1 centipoise. So when I look at the centipoise as a unit, water is normalized, it's 1. So that's, everybody kind of likes using that because I have a reference to water immediately, and water is something that we all have experience with. So can you calculate what is the conversion between SI system and CGS system? So 1 poise is how many Pascal seconds, or 1 centipoise is how many Pascal seconds. For that, you of course have to know conversion between dyne and Newton. And since you probably have your devices with you, you can find that out. Or the book. And there's a hint down here. So again, I want how many Pascal seconds are there in 1 centipoise? There we go. Did everybody get a chance to get that number? Okay. All right, so 1 centipoise, which is viscosity of water, is 10 to the minus 3 Pascal seconds. Okay. So this is the conversion. So 1 Newton is 10 to the 5 dynes, and that gives you that 1 poise is 0.1 Pascal seconds, and then 1 centipoise will be 10 to the minus 3. Okay. In British system, you will actually have 1 pound per foot square, and velocity is foot per second times 1 over foot. Okay. This is pound mass, okay, times foot per second square. So pound mass, there could be pound mass and pound force. Have to distinguish between the two. So in British system, you will have pound mass over foot times second.
Is pound and pound force?
Pound force is the equivalent, the force, gravity force on 1 pound mass.
Is that the pound then?
So this is pound mass. Yeah, pound is pound force. Okay. So now let's look into some questions. Now that we defined the viscosity, we need to know something about it. Okay? So true or false, viscosity of liquids decreases with temperature. What is the some everyday example of that happening? Eating?
Heating up honey.
Right. So I can heat up honey, or better yet, if you're in Texas, you're going to heat up some oil and make some eggs in the morning. Okay? So basically, you know that oil on your pan when you're making food is going to move faster, meaning that viscosity decreases with temperature. All right. How about gases?
False.
It's actually false. So that's kind of interesting. Okay. And we can just go and measure this and take it as a fact, or we can try to understand what the mechanism of this is. Okay. So if we're trying to understand what the mechanism is and answering this question why, we need a theory. We need that mechanism. So just by observing nature, okay, I will have to come up with what is something underlining it, what are the rules, if you will. And that's what typically theory gives me. So we will actually go into, so these are experimental observations, and we would like to have a theory that will actually give me this theoretical prediction, if I get it right, that viscosity of gases increases with temperature. So you can actually, I simply plotted the experimental results from BSL in table 112. Okay. And you can see that there's a temperature in degrees Celsius and there's viscosity in millipascal second. Okay. And you can actually see that for gases, I actually have increase with temperature. And for liquids, we can actually see a decrease, and in the range that they were looked at, it's not linear, so it's something more complex is at play. So a good theory that would unify both would explain both of these. Okay? And theory means that I have some way to predict, like some formula that can, given other measurements, temperature being one of them, I can actually have the explanation. Okay. So essentially we have, this is for water. So at 20 degrees, this is our favorite number of 1 centipoise, which is millipascal seconds. But it's higher at 0, and it decreases as I go basically nearly 5 times. Okay. All right. So for your reading, please go to chapter 1.1, and next will be chapter 1.4. So I will actually just start, I think I'll just test my system because I will start writing next time without starting the entire, I can start a little bit of it and then I'm just going to repeat. I would like you to read chapter 1.4 before Wednesday. Okay? It's just going to be, you're going to get much more out of the class if you read it through, because I don't think most of you were exposed to these concepts. And I'm just going to quickly start it. If I can communicate with my, okay, I'll be back in a second. So basically we will start actually from 1.1, we will go to chapter 1.4 on molecular basis for viscosity, first of gases and then of liquids. So our motivation is explaining the difference that we see. So we are looking for theories that could actually explain this experimental observation. So what we will do, okay, we will assume that we have two parallel plates, so we will fit ourselves into our Newton's law situation, the basic situation, and we will impose a gradient in velocity. So we will assume that this entire plate below is moving at velocity Vx, and that the upper plate is kept still, and I have gas in between, and this gas will be idealized gas. So the simplest situation possibly that I could have is so-called kinetic theory of gases, where I have, you can imagine bouncing balls like tennis balls, okay, where any collisions that I have are completely elastic. We know they're not, okay? And the only, anything that is happening is the result of these balls colliding. So there are no other forces at play, such as polarity of molecules, electrical forces. None of that is happening. I just have balls bouncing. Okay? So this is the simplest theory of gas, and it's called kinetic theory. And it explains gases at low density rather well, and also gases that are not polar in nature, so simple molecules. And it's also the only theory where we can actually compute something on paper. Okay, in anything more complex, especially when I have electrical forces that are at play, it becomes extremely difficult to do the calculations. Okay. And we will then see, if I assume kinetic theory, which is essentially independent from anything that Newton has observed. Okay, he didn't think about kinetic theory when he observed that we have this linear relationship between stress and the difference in velocity. So basically, then we will actually try to see whether we can independently confirm that the Newton was right. And that, if we do that, that really, really strengthens the observation. And that's how actually something becomes a law. Okay? So that means that we actually have a fundamental mechanistic explanation that comes from a completely independent source. Kinetic theory is a molecular theory. Okay? Newton's observation was not molecular, not in 17th century. Okay? Maybe now we can have molecular observations, given the microscopes and spectroscopy and whatnot that we have at our disposal. But now, back then, that was not the case. So if I can independently confirm his observation, then actually we're really onto something. So again, just as a recap, if his observation is to be confirmed, then basically I will go and attempt to compute tau yx using kinetic theory, okay? And I should get that tau yx and dvx dy are related in a linear fashion. So this mu, I'm not going to get mu, I'm not going to assume that I have mu, because then I assume Newton's law, so I'm going to confirm it if I assume it, right? But I will get, it's like I'm just going to get what I thought I'd get anyway. So essentially, I'm not going to assume I have mu, but I should get some bunch of some other constants, okay, that will actually also give me a formula for viscosity, given some other macroscopic observations, like temperature. Okay, or pressure, or something else that I mentioned. Okay. So again, we're going to try to compute tau yx, and I should get that tau yx is a bunch of some constants that do not depend on velocity times dvx dy. So the only velocity dependence should be here in this gradient. Okay. If I get that, then I have confirmed Newton's law, and that becomes a really strong result. So I will just introduce the kinetic theory, and then we'll do the computation later. So in this kinetic theory, we assume each molecule is a rigid ball. There are no attractive forces between balls at all. Okay. In reality, we know there are. These gas molecules are in constant randomized motion. Okay. And I have elastic collisions between them, meaning that I'm not losing any energy when I collide. Okay. So all of the macroscopic properties, we're used to looking at pressure that way. Okay? So pressure and temperature that we measure are a result of these collisions. Okay? And distances, this is going to be a rarefied gas. So distances between molecules are large, but there are still enough, when I put these two plates, I will have enough molecules in there to actually integrate and upscale. Okay? So I have enough molecules for any statistical formulas to actually be valid. It's not that I'm bouncing 10 molecules around. Okay. So that's essentially, those are going to be our assumptions. And as we will just take, I'm going to flash them to you and then stop. So we will look at kinetic theory, basically integrates these assumptions and distributions of velocities and so forth. And you will in your homework have an example of how that's done. But basically, you then get that mean free path between two molecules colliding is related to the diameter of these molecules as well as their number density. Okay, so you will get, like, we will use those results from the kinetic. So we will continue this discussion on Wednesday. Please read chapter 1.4 before we go.